Okay, so this would be like section 11.4, where chapter 11 deals with relations. So I want to kind of first just start with page 2 of this document, which defines a partition of a set. And so for anyone that maybe has taken a probability course or something else, you might have seen these partitions in other classes. So a partition of a set. So we have a set S, and P is a partition. It's going to be a set of subsets. That's what we're going to call a partition. And in order for P to be a partition, there are going to be a couple of properties that need to be satisfied. So one is each of the subsets is pairwise disjoint. So basically, this partition is going to be made up of a bunch of sets. I'm just going to call them A1 up to AN. So each of those sets AI is a subset of S. That's kind of the first thing. And this is going to have this property to say pairwise disjoint means if I take any two subsets that are any two distinct subsets in this partition, their intersection is the empty set. So we've got kind of one property over here. That's the pairwise disjoint. Okay, we need them to be non-empty. So that means each of these sets in the partition, right, needs to contain something. Is not the empty set. And kind of the last one is the union of all of these sets should give us back S. So just to kind of clarify this, okay, so first of all, each of these things is a subset of S. Secondly, each of these is non-empty. Secondly, each of them should not be the empty set. Another condition is their intersection of two distinct subsets in the partition should not contain the same element, so they should be empty. And the fourth one is if I take A1 union A2 union A3 all the way up to the nth one, we should get back the set S that we started with. So really there's three conditions, I'll say. Like number one, it's not something we necessarily need to check. That's usually pretty quick to see if we've got it. So kind of the short story here is for P to be a partition, each element in our original set S should appear exactly once in one of the sets. in the partition. So therefore, if it only occurs in one of those sets, that's going to ensure that the intersection of any two sets is empty. And we want to make sure that each element appears in exactly one of the sets so that when we take the union back together, we get S. Okay, any questions about that definition? Okay, so I'm gonna open up, sorry, I never hit that button before. That was interesting. Okay, sorry, we're gonna, I'm gonna open up this poll again that says, is it one-to-one? But what I'm asking here is this first example in part A, is this a partition? So yes or no. So yes would mean that it is a partition. No would mean that it's not a partition. Okay, great. Thanks for the replies. So everybody says yes, this is, and yes, this is, right? So here what we want to make sure is we've got our set S over here is first 6 integers, or first 6 natural numbers, I should say. And so what I can see is all of, when I take the union of 1, 3, and 2, and 4, 5, 6, we get S back. So that checks out. We can check that none of these sets in the partition share any elements in common. So this intersect with that would be empty set. This intersected with that would be the empty set, and so on. So they are disjoint. And none of the sets are empty, right? So that satisfies all of those conditions. They're all subsets of the original set. So that's a yes. Good. Any questions? Okay, what about B? That form of partition. Okay, so here we're feedback there. So people were saying that one looks pretty good. That's right. So I'm just kind of writing out what this partition would look like. So that would be all the even numbers grouped with all of the odd numbers, and a second set with all the odd numbers. And so these are disjoint, right? A number can't be even and odd at the same time. And all of the integers have to be either even or odd. There's no third choice. So when we take the union of these, we'll get all of the integers back. Okay, let's take a look at one more example of this. Let's try C. Whoops. Let me relaunch it. So you think this is a partition of the integers, or excuse me, of the natural numbers or not? So here we've got primes, we've got composites, and we want to know, can we partition the natural numbers into primes and composites? Okay, so here were the results. Though someone chatted in, they wanted to change their vote from a no to a yes. So either way, things are pretty divided here. So this is actually not a partition, and the reason why might be getting into the nitty-gritty of what it means to be prime versus composite. So for someone that said no, definitely, or maybe I'm not certain, why would this not form a partition of the natural numbers?
Because one isn't prime.
Good, that's right. So the number 1
or composite.
is not prime or it's not composite, right? It's kind of a special number when it comes to that. So if we want to partition the natural numbers, we would need to put 1 in here and then the primes and then the composites. So 1 is not prime and it's not composite. So a number is prime if its only divisors are the number, it's kind of defined as P is prime if P is not 1 and its only divisors are 1 and itself. So it's more of a bookkeeping thing in mathematics. You could ask, why did we decide not to make 1 a prime number? I don't know, just the way it was done. Okay, any questions about that? Okay, so that's the notion of what a partition is. So part of this quiz that you guys are going to have to do on Monday after the exam is going to ask you about the definition of a partition. Is this thing a partition? This sort of stuff. Okay, so now let's relate this back, this notion of partition, back to equivalence classes. So we say an equivalence class of A is going to be the set of all numbers or all elements that are related to A. Yeah, so for example, the one that we just did, question 5 on worksheet 18, was asking us about the smallest element relation. Where X was the set of the first 100 integers, natural numbers. And we said this was an equivalence relation. And then you can think about the equivalence class 1 would be equal to the set of all elements such that X, in this case A, is related to 1. So in other words, it would be all subsets of X be all subsets of X that have 1 in it, the number 1 in it. Since if 1 is in it, it has to be the smallest one. So these equivalence classes is a set itself. Okay. Let me just say, we'll see that there are different ways that we might denote an equivalence class. We're going to say that A is the representative of this class because it's the element that we're using to describe the class, right? We're saying that this is the set of all things that are related to A. And so if we think about this smallest element relation, right? These two equivalence classes, what this theorem is saying is because this smallest element relation is an equivalence relation, the corresponding equivalence classes should be the same no matter which element I pick from that equivalence class. So the set of all things that are related to 1, the set 1 should be equal to the equivalence class, which would be the set of all things that are related to 1, 2, since these guys have the same smallest element. So what this theorem is saying in 2 is that equivalence classes are super nice. This is not true for any relation, but if your relation satisfies these 3 properties, reflexive, symmetric, transitive, then it is going to be true that if 2 things are related to each other, then their equivalence classes are going to be equal to each other. So in other words, it doesn't matter what representative we pick to express the equivalence class. This is not true for relations that are not equivalence relations. Okay, so here, a couple of things to note is this is an if and only if statement. So this is a biconditional statement. So there's 2 things that you would need to show, and that is if equivalence A is equal to equivalence B, that's going to imply that A is related to B. And then we would need to show the other direction, which is if A is related to B, then then their equivalence classes are equal. But the short story here equivalence relations give us nice, well-defined equivalence classes. So in other words, it doesn't matter which element from the equivalence class we use as the representative. So maybe rather than prove this theorem, which we'll get to, let's just do an example together. And not worry about all of these proofs here. Yeah, maybe we'll take one from your homework assignment that I removed. So let's consider the following relation. So this is on your homework assignment that you're working on for today, number 3, which first asks, we're going to let R be this relation which we're going to define on the set of integers as follows. We're going to say that A is related to B if and only if A plus B is even. So on your homework, you prove that this is an equivalence relation that it satisfies those 3 properties. Let's take that for granted. And now the second part is what are the equivalence classes? So let's just kind of think about what one of them might look like. So if we take the integer 0, this would be the set of all integers such that integer k is related to 0. So what would be some elements in this relation, in this equivalence class, I should say? Can someone tell me what's another integer that would be related to 0 by this relation. Let me just replace k related to 0 with what that means. What's an integer that when I add it to 0, awesome, 2, oh, thank you, I saw 1, 2, 4, 6, 8. And here we have integers, so we have negative numbers too, right? So if I'm listing this out, be the set of all the even integers. And because this relation is reflexive and transitive and symmetric, right, we could think about, well, what would the equivalence class of 2 look like? Well, it would be all of the things, all of the integers, such that when I take it and add it to do, we get something even. Okay, so that's what we mean by saying equivalence class of A is equal to equivalence class of B. So in other words, it doesn't matter which thing in this set I choose to be its representative, they're all going to be the same. So the equivalence class for 2 equals the equivalence class for 0, right, equals the equivalence class for 100, equals the equivalence class for any other even integer. So this equivalence relation, two integers are related if their sum is even, divides the integers up into two equivalence classes, right? One of them, all of the even integers, one of them, all of the odd integers. Which are the even and the odd integers, which we already checked when we were talking about partitions, that this is a partition of the integers. So kind of one result that we'll prove next time is the equivalence classes that I can now represent in terms of their equivalence classes. So this forms a partition. Since this is all of the even integers, this equivalence class is all of the odd integers. Okay, so I will, I'll stop here and we'll pick up from this point after the exam. Anything that we talked about with equivalence classes or partitions, you guys won't be asked about that on the exam on Wednesday, but we'll pick up at that after the exam. I wasn't planning on I'll open the quiz after your exam. So let's not worry about this. Focus on getting ready for the exam on Wednesday. After the exam, I'll open up a quiz that's just going to ask you about some definitions that we just talked about. And I'll just post an announcement to you all just so that you remember to take the quiz over next weekend, so that when we come back on Monday, we'll have this stuff fresh in our minds and we'll be able to hit the ground going. Okay, well, if you guys have any questions about the homework or getting ready for the exam, Lindsay has office hours today, right? And I've got them tomorrow. So Lindsay, when are your office hours for today?
Today they're from 1 to 2, and then I also have them on Wednesday before the exam from 9 to 10.
Okay, and I've got mine tomorrow from 1:30 to 2:30. Yeah, that's mine tomorrow. So yeah, so you're welcome to stop by our office hours. Yeah, good luck getting ready for the exam otherwise, and I will see you guys on Wednesday. If you can get into Zoom a little bit earlier, maybe 5 minutes early on Wednesday, we can just go over the instructions and make sure that we get the exam started on time. Yeah, otherwise, good luck getting ready, and see you guys on Wednesday.